All right. We'll go from current slide. Okay, once you get the book and listen to the video, because everything, I went over everything in it. Sorry, this fell on the floor. Okay. All right. Those of you who were here then, we'll start from current slide. Any questions on anything we did last time? Okay, and if you do get your book, and you see, we went over all the other stuff, and then we started in chapter 5. And I talked about which one. 5, we didn't get very far. We went through 5.1, and we're just starting on 5.2. So no homework assignments yet. It will be today, but you know they're all for you to do. You don't have to turn them in, but it's that. Now, the Screencast-O-Matic records everything I say that gets picked up by my computer microphone and everything that's projected on the board. Like I said, it doesn't get where I'm pointing to because that's not on the system. Okay, so let's start with, if there are no questions from last time, at least one more person came in. And let me get you marked on the roll. There's only one, right? And you are Cerdarius? Okay. That's what I was going to guess, but I wanted you to tell me so I wouldn't be guessing wrong. All right, so we got 6 people here, right? Okay. Now, last time we talked about forces and the law of inertia, which happened to have been Newton's first law of motion. So that's all there. You can hear about it on the YouTube video once that link gets established again. Okay? 5.2 starts with force and the law of acceleration. This is basically Newton's second law. Newton had 3 laws that he did. The first is the law of inertia. Second, this is calling the law of acceleration. And then the third one is the law of action and reaction. And we'll get to that, I guess, later in the next section. So the law of acceleration, the total force, okay? Remind me what a force was. Push or a pull, exactly. A force is a push or a pull. The total force acting on a body is equal to, so this is the easiest way to remember the second law. Oops, let me get my pen set up. Okay? And it says the total force, most physics would call it the net force, okay? And we'll talk about that in just a second, is equal to the mass times the acceleration of the body. That's Newton's second law. If you have a net force acting on an object, it's going to move. And it's going to change its motion. That's what acceleration is, the change of motion. The first law, the law of inertia, is if there are no net forces acting on a body, it's going to continue its line of motion, straight line motion, constant speed, no turns, no anything, unless it's acted on by an unbalanced force or a net force. But if there is a net force acting on it, then according to the mass of the body, the net force will be the product of the mass times the acceleration. Now, what is acceleration? Do you remember that from last time? Change of velocity per change of time. The time rate of change of velocity. Velocity is movement. Okay? Velocity, remember, has direction and speed, so it's a vector quantity. So for a constant velocity, constant direction, constant speed. If it's changing anything, changing its speed, speeding up, slowing down, or changing direction, that's acceleration. It has to have acceleration to have a change of velocity. Now, if it does have an acceleration, there must be a net force acting on it. Now, what is the mass? What was that related to? Did we talk about that last time? That's related to the inertia. Remember I think I gave the example of a ping pong ball and a bowling ball. Certainly a bowling ball has a lot more mass, so it would have more inertia. So if I threw a bowling ball at anyone in here, you're going to have to exert a lot of force to get it to stop before it hits you. Ping pong ball, it might not even make it there. There's enough air resistance to create the force to stop it. Okay? So the greater the mass for a constant force, the less the acceleration. Okay? And for a constant force, the lower mass is going to have a greater acceleration. Okay? Or, for a constant force, same acceleration. Well, we could change that around. And remember, I told you 3 ways we could rewrite any of these equations. What are 2 other ways to write this one? Okay. The one, we could divide both sides by mass, and then you have acceleration is equal to the net force, or the total force this book calls it, divided by mass. So there's a second way. Oh, we didn't do it? I didn't show you the triangles and circles? Oh, okay. I'll do that then.
Because I remember you saying when you do the distance divided by the time.
Yeah, okay. And every one of those that is a product or a quotient you can do in this method. The third one would be mass is equal to net force divided by acceleration. Now, we don't use that one very much. But you could do it if you needed to. But, like you just said, let's go back and do that. Velocity is equal to change of distance over time. Acceleration is change of velocity over time. And every one of these you can write 3 different ways. This one could be distance is equal to velocity times time, or time is equal to distance divided by velocity. Same thing here. Velocity is equal to acceleration times time, or time is equal to velocity divided by acceleration. No, yeah, right. Yeah, you're doing the same thing. Okay, now, let me show you sort of an easy mnemonic device to remember this. I learned, my physics, my formulas and stuff like this, and to me they made sense. But when I was in the U.S. Navy and went to Navy schools, I found out they had little shortcuts to help even sailors remember what these formulas were, okay? And here's what they said. You can either use triangles, I like triangles, or circles. I like circles fine too, but I think triangles work a little better on this one. And they really set up the same way. It doesn't matter what the shape is. Whatever thing is on top or is the product of the 2, for instance this one, be net force, is equal to mass times acceleration. I say acceleration and write an X. Where did that come from? I don't know. And the X eraser's not working. There we go. All right. Acceleration. Okay? And here's how you use it. And you could do the same thing in a circle if you like circles better. Net force, mass times acceleration. Okay? Let's see how you get all of those out of it. The first one, the first one here, you cover net force, mass times acceleration. There it is. Right there. And if you're looking for the acceleration, cover the A and you get net force divided by mass. And if you're looking for mass, cover the M and it's net force divided by acceleration. There it is. So you call this the vertical line the multiplication line and the horizontal line the dividing line. Okay? Now you can do it with circles or triangles, whatever. And every one of these, and we'll run into several formulas that are just like this. Okay? Let's change for the one on up there. Okay? Let me change my the top one. You tell me where to put what. This one right here. Any one of those 3. Tell me where to put what. Whoa. Somehow, I don't know how that happened. Okay. Say again? What goes on top? Okay. Think, if you see it as a dividing line, whatever's on top has to be on top. So what has to be on top here? D. Okay? And then what goes on the bottom? V and T. Perfect. Okay? V and T. Okay? Now, let's do the same thing for acceleration. Okay? Yeah, okay. Notice I left T down there because T's in the same place. So what goes where? Velocity on top. And what? Acceleration down here. Perfect. Velocity is equal acceleration times time. Acceleration velocity divided by time times velocity divided by acceleration. Anytime you have that multiplication or division principle there, three quantities and they're multiplied or divided, you can set them up and use this. Okay? It makes it pretty easy to do. So there's Newton's second law. If a body's accelerating, there must be a net force. If there's a net force on the body, it's got to be changing its motion. In other words, changing its velocity, which means accelerating. That could be speeding up, slowing down, or just changing direction. All those are forms of acceleration. Okay. Now, let's talk about units. Okay? We talk about what the unit for a mass is. Okay. Unit for mass in the SI system is a kilogram. Now, you would think it would be a gram, the basic unit, but SI system uses kilogram. Basically, a gram is about the mass of an aspirin tablet or two. It's just so terribly small. A kilogram would be, well, this probably is 1.5 to 2 kilograms. So that's a more normal. It's not a tiny amount of mass. It's a more normal. So the basic unit in the SI system, now y'all know what I talk about when I say SI or not? Okay. There's many other systems. Have y'all done, any of you done pharmacology? Oh, you haven't? Okay. There's all sorts of different ways to measure things. But the two that we're most familiar with is the U.S. customary. It used to be called the British or the English system. And that basically that's what we use every day. Inches, feet, yards, pounds, ounces, those kinds of things. In the SI system, there's a little bit of history here. And here's basically what it was. For much of European history, much of it, not all of it, the two big powers were usually England and France. Britain and France. Okay? Now, not always. Germany was very powerful sometimes, and a few others. Spain was powerful at one time. But for much of the European history, it was Britain and France. And guess what? They're right across the channel from each other, and they fought like cats and dogs. Okay? They just couldn't get along. If any of you have ever seen the movie Chariots of Fire, it was about Olympics back in the 30s or something there. It just showed, that movie illustrated pretty well how much the English disliked the French and the French disliked the English. Okay. So anyway, that's why I brought that up. I thought maybe someone had seen it. Well, England was a fairly small, compact country because it's an island nation, right? So therefore, they control things pretty well. So they had their units, and this isn't necessarily where it came from, but an inch is approximately your thumb joint, your first thumb joint. That's approximately an inch. At one time, they said it was 3 barley coins laid end to end to end was an inch. Well, that's about like that. A foot, guess what? Pretty close to what a man's foot was. That's pretty close to a foot. A yard was, done this way, approximately the distance from your nose to the tip of your finger when you hold your hand out there. Have any of you ever been in the old hardware stores where they sold fabric and saw the little old ladies that were measuring cloth for you? And they said, I need 5 yards of muslin or something like that. They go, 1, 2, 3, 4, 5, and then give you a little extra in case the arm is short. Because that was about a yard. Nowadays they have the tables and it's all measured exactly. But in the old days, I can remember seeing that happen. Okay? So So that's about a yard, okay? The relationship between these things are rather bizarre. How many inches in a foot? 12. So how many feet in a yard? 3. How many yards in a mile? 1,760. Where do these numbers come from? They don't make a lot of sense. But that's because historically they came about in different ways. So let's go to weight. How many ounces in a pound? How many ounces in a pound? Oh, come on. 16. Not 12, 16. 12 inches in a foot, but 16 ounces in a pound. Where are these numbers coming from? How many pounds in a ton? 2,000. Well, finally we got a round number that's easy to remember. But where are these other numbers coming from? Well, they came historically from different things. See, some king said this was a yard. This is from his nose to here. Well, I see. If Shaq O'Neal was king, well, it would be a long yard, wouldn't it? Okay, so obviously that wasn't the best one. But it worked for England. Now, France tried to have something like that. But you see, France was a big country, all spread out. There was Normandy, there was Brittany, there was Alsace-Lorraine, there was the region around Paris, there were all these different things. And these people like to cheat the others. So they would change their scales, and they couldn't keep anything even. And France was beginning to have some problems. Anyone know what happens in France about 1791? What was that shortly after? What happened in the U.S. before 1791? Like 1776. The American Revolution. Okay? We did that. And because we were fighting against England, the French helped us because they didn't like England. Okay? That's how politics ran back then. So what they did, and they were so inspired by our revolution against the English, they decided a few years later to revolt against their monarch. Louis the 16th, was it? Marie Antoinette, the guillotine, and all that stuff. It was not a pretty time at all. But the French Revolution was not nearly as simply done as ours was. We were fairly civilized with ours. If the revolution could ever be civil, they were not. They just executed people like crazy. People that had been supporting the revolution, they said you didn't support it bad enough, cut their heads off. Yeah, it was awful. Okay, not a pretty sight at all. So, but about that time, since all that upheaval was doing, and France had not been able to, all the different regions were cheating each other, they came up and said, stop, time out. Let's come up with a new system that doesn't depend on anybody's body parts or anything else, and come up with something new. And they came up with the metric system. And metric means to measure in French. To measure. Metric, that's all it means. So if you see geometry, that's the measure of the earth. Metry at the end. Trigonometry, the measure of triangles. Anytime you see the metra at the end, that's metry or something like that, that means a measure. So they came up with the metric system. And they took as their fundamental length that nobody could dispute was the distance from the North Pole to the equator on the surface of the globe, okay? And they took 1/10,000,000th of that or something like that and said, that's a meter. Nobody can contest it, okay? And they had a standard meter. Now, approximately, this is what a meter is. A little bit longer than a yard, so it goes from the opposite ear to the tip of the finger, approximately. In fact, most doorknobs are very close to 1 meter above the floor. Okay? It's not absolutely necessary for them to put it that way, but that's just standard. That's about what they are, about a meter. So you can estimate a meter that way. Okay? And then they did all the other units based on that. And then they had the prefixes for the units. Like we have some that we don't use very much. A decimeter is, a decimal is a tenth of a meter. Okay, if a meter is this long, 1/10 of that, think about that. Okay, a centimeter is 1/100th of a meter. So that would be about the width of your little fingernail. A millimeter would be, they didn't use this, but just to give you an idea, about the thickness of a dime, is a millimeter. Okay? So that's 1,000th of a meter. If you took 1,000 dimes, that would get from here to there. Okay. So that's what these are. Then when you go up, a decameter, what's a decade? 10 years, so a decameter would be 10 meters. Okay, so that'd be 10 distances there. And then a hectometer would be 100. We don't use that very much except in measuring land area. And then a kilometer or kilometer would be 1,000. Now, anything less than 1,000, which would be a millimeter, and anything greater than a kilometer, which would be 1,000 meters, we go only by powers of 3. You know, they don't use the individual ones. Okay. So then after millimeter, you have micrometer, which would be, basically, take that dime and imagine slicing it into 1,000 equal slices. That's 1 micrometer. Okay? Take that and divide it into 1,000 equal pieces, and you got a nanometer. That's about the distance between atoms in a molecule. I mean, it's really, 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 really small. Let me get you here if I can get the right piece of paper and my right pen. And you are, second?
Jameson.
Darius?
Jameson. Trenton Jameson.
Oh, okay. Trent, right?
Yes, sir.
Okay. My hearing is so bad, I apologize. Okay. Everybody else, I think, has gotten it. Okay? So those are the metric things. Okay? Well, what they used for the basic unit of mass when they first came out with the metric system, because a meter was so big, okay? If you think about this, if this door handle is about a meter off the floor, this door is about a meter wide. And if you came out here about a meter here, that would be about that far from the door. If you imagine a block that was that tall, that wide, that deep, that's a big block, a huge block. Well, that was just a bit too big. So they didn't use a meter, they used a centimeter, 100th of a meter. And by the way, centi, how you can remember that? I don't think I have one in here. What's the little odd-colored coin that we have? Not a dime, not a nickel, but a penny. And what's the value of that? 1 cent. What does that mean? 1/100th of a dollar. A cent a dollar. We just say a cent. 1 cent. So that's 1/100th. A centimeter is 100th of a meter. That's about this thickness. Well, if you take a centimeter thick, a centimeter wide, and a centimeter deep, that's called a cubic centimeter. Those little bitty blocks of sugar sometimes you have that don't really sweeten anything, that would be a cubic centimeter. Okay. Now, the amount of mass of water in that 1 cubic centimeter, that's what they call the gram. That's what I said. That's about like an aspirin tablet. It's a very small amount of mass. Well, that wasn't a good thing to use as the basic unit, so that's why we use kilogram, 1,000 of those. Now, 1,000 of those would be what you would have in 1 liter of water. Don't see any liter containers in here. That's probably something about 24 ounces, your cup there. What would you guess? Is that about right? Okay. I think 59, about 2 of those would make 1 liter, approximately. Maybe a little bit more than 2 of those. Okay, that would be a liter. That would be a kilogram of water. Okay? So, a massive kilogram, okay? And by the way, I guess I'll go into this a little bit too. Let me go with a new slide. Okay? Since we're covering some new material here. Okay? The fundamental units that we measure are mass, length, time, temperature. We're not going to mess with temperature much in this class. Mostly those. Oh, no. Electrical current would be, the symbol for that is I. Where that comes from, I don't know, but it's capital I. Okay? Candela is light intensity. We're not going to mess with that any. Moles are a quantity of chemical quantity. We're not going to mess with that any. And that's it. Those 7. Okay, this is mass. This is length. This is time. This is temperature. And this is current. It doesn't have anything to do with I, but that's what it is, current, electrical current. We will be dealing with that in a later chapter, okay? Now, those are the fundamental units. All other units in the world come out of those 5 and the other 2 that we're not talking about now, okay? But most of them come out of these 5. So let's say velocity. What is velocity? We just did that a little while ago. What was that? Distance over time. That's a length divided by time. There we have it, based on those units. And what was an acceleration? V over t, but velocity was distance over time. Over time, that would be a length over time squared. That's what an acceleration is, a length per time per time. Okay? So anything you measure is based on these fundamental units. Okay? So, let's go back to our force. We're going to figure out what that is. That's mass. And what was mass? We said in SI unit, that's kilogram. Okay? The basic unit for mass, SI system, is kilogram. Now here's an aside here. Sorry to be breaking this up. But in the U.S. customary system, that usually called the British or the English system, no one measures mass to speak of. We measure weight. Weight is a different quantity from mass. Weight is a force, which we're going to get to in just a minute. So what is that? There is a unit, but no one ever uses it. Does anyone know what that unit of mass is in the U.S. customary system? You've never used it, except for talking about something else, and it had nothing to do with mass. A slug. A slug. S-L-U-G. That is the unit of mass. You've never gone to the grocery store. I'd like 3 slugs of potatoes, please. They would look at you and say, what? If you said 3 kilograms, oh yeah, we'll get the scale and measure. But that's the mass in the U.S. customary. We always talk about weight in the U.S. customary system, not mass. So that's bizarre, but true. Okay? No. I'm not going to say none of the problems would do, but none of your test problems I don't think will have anything to do with slugs. Slug is not used. Everything else, like kilogram, kg, inches is IN, feet is FT, miles is MI, hour is H, second is S, minute is MIN, meter is M, millimeter is MM, centimeter is CM. Everything has an abbreviation, right? Except slug doesn't. No one uses it, so if you use it, you have to write it out. Okay? It doesn't even have an abbreviation. No one uses slugs. Okay, so forget about that. So mass is kilogram. And what do we say? It's mass times acceleration. So this is a kilogram times acceleration, we said, was a length divided by time divided again by time, so we say time squared. Well, let's put units there. I've been putting parameters. Let's put the actual units there. Length in the SI system is a meter. The basic unit of length in the SI system is a meter. So kilogram meter, and time is seconds per second squared. That's what a force is. A kilogram meter per second squared. Mass times acceleration. Now we actually give that its own name. Does anyone know what that is in the SI system? Named after Sir Isaac. I'm sorry, like this. That is a Newton. And since it's named after somebody, we make a capital M. Notice Kilogram's not named after anyone. Meter's not named after. Second's not named after anyone. Those are lowercase letters. A Newton's named after someone, so that's capital letter. Capital N is Newton. A kilogram meter per second squared. Now these are the units. Kilogram meter per second squared. The parameters are mass and acceleration, M and A, force. The unit for this is Newton. The unit for mass is kilogram, and the unit for acceleration is meter per second squared. So sort of get in your mind, you have the parameters, F, M, and A, and you have the units. The units always have numbers in front of them. 7 newtons, 3 kilograms, 15 meters per second squared. That's a really fast acceleration, by the way. Okay, so what we did here, what I did was sort of catch you up, because in the earlier chapters they talked about this, is a Newton is a kilogram meter per second squared. Now, in the U.S. customary, the unit for force is pound. Now, if you had to give a unit, and this is where they get it, a pound is, the mass is a slug, you can't even have an abbreviation for it, foot per second squared, because the basic unit for length in the U.S. customary system is not the yard, but the foot. Okay, so a slug foot per second squared. You never use slugs. You use pounds all the time, so just use pounds. Okay, slug foot per second squared. All right, that's all the background. Now we go to our first example ever. Now these examples are going to be very similar to the problems at the end of the section, and they're going to be very similar to what your test problems will be. So get these. Get them good. I can't find there's my cursor. Okay. Example 1. This is on page 126 if anyone has a book. What force, okay, now I'm going to start it off doing this. I won't do this on all of them. I'm going to write the problem for you. What force, I don't write very well either, and I wind up abbreviating like crazy, is necessary, that's going to be enough for necessary, to produce, that'll be it for produce, and acceleration, that'll be acceleration, of 6.00 meters per second squared. There's the right units, aren't they, for an acceleration, on a mass of 5.00 kilograms. There's the problem. Okay? Now, let me explain a few things about the problem. And this book is pretty picky about it, but I'm not going to be as picky as the book is. Okay? Do I need to do it?
The
6.00. I slashed my zeros. That was a habit I picked up in the Navy. When you're keeping a log, an O is a O, and a zero looks just like it, so you had to slash the zeros to distinguish it from O's. When I write a Z, I always slash the Z to distinguish it from the S, because that could look like an S. When I draw a 7, I put a slash through that too, so you don't think it's a 1 with it. No, so I do those things just left over from the Navy. Okay. Now, why 6.00 meters per second squared? They do this to indicate the precision of the measurement. That is incredibly precise. That means to the nearest hundredth of a meter per second squared, that's what your acceleration is. And to the nearest hundredth of a kilogram, that is your mass. So that's just telling you how precise your measurements are. Now, why is that important? Because when you're doing manipulations with it, you can't get more precision out of an operation than you put into it. So our answer, whatever it's going to come, will need 3 significant digits. You have 1, 2, 3 significant digits, 1, 2, 3 significant digits. So that's why they put the zeros there, so it indicates significant digits. Okay? Now, when I'm working a problem, here's where I begin. I look for, what are they looking for? What's the question here? What are we looking for? Read the question. We're looking for force. What force? There's the question right there. What force? Okay, so there's what we're looking for. And we can understand that to be net force. Okay, to produce an acceleration of, well, they've given us that. What symbol do we use for acceleration? A. And that acceleration is 6.00 meters per second squared. Okay, here's another timeout here, sorry. Units are very important. Let me give you just a, I hope it won't be too long of a story, but it's a true story, except I don't know the exact numbers. Okay? Back in the 60s, wasn't it? We were in, well, back then, the U.S. and Soviet Union were the two big world powers. Okay? And both of us had done something. Back in the 40s, we defeated Germany in World War II. And Germany had the top scientists in the world. Okay? And we were very fortunate that some of those scientists, even before the war, came to the U.S. What was Germany like then? Does anyone know who was ruling Germany in World War II? Second? Hitler, exactly. And what was he most infamous for? Yeah, killing Jews. Is that what you said? And that's why, and a lot of the really bright scientists in Germany were Jewish. Now, if they had a choice, they could go to England, they could go to France, they could go to Russia, or they could come to the U.S. Those were the big four powers there. They didn't want to go down to Italy. Why? It was fascist too under Mussolini. They were in it with Hitler. They didn't want to go to Italy. Okay, Spain was kind of neutral. They were pretty fascist too, so didn't want to go there. So that's where they had choices to go. Well, when the war broke out, France went down pretty quickly. Britain was getting beaten up like crazy. Russia was having some problems too. U.S. was way over here. And we were the land of promise, you know, brand new country, or fairly new country compared to the others. So a lot of them chose to come here. Thank you very much. Okay. Anyone remember any that may have done that? Einstein was one of them. You're absolutely right. Many others like Einstein came over, and we benefited greatly from their knowledge and experience and expertise coming over here. Well, after the war, and what the Germans had done, why Britain got beaten up so badly, they had developed rocketry. They could fire rockets from very northern part of Germany or some of the other countries that they had conquered and hit Britain. And they were just pummeling Britain, you know, and just beating the tar out of them. But Britain held on. Good old Winston Churchill, never give up, never give up, never give up. And sure enough, if it hadn't been for him, we may have gotten into the war too late to stop it. But he kept Britain in there. Thank goodness they were out in the country. They couldn't invade by land, and they had a strong enough navy that they could keep them out. So anyway, but they were sending those rockets over there. So all the other countries were salivating, wanting to get that rocket technology. So when the war was over, Russia grabbed all the rocket people they could, U.S. grabbed all we could. You know, and France and Britain got a few too. But that started the space race. Because a lot of those German rocketeers, rocket scientists, really didn't want to fire weapons at people. They wanted to go into outer space. That was their goal. But they wound up having to build rockets to kill people. And have you ever heard of Oppenheimer? Who's the one up in Huntsville? Their civic center is named after him. Von Braun, Werner von Braun. They were some of the ones we ripped off from Germany, came over here and helped us. Well, Russia and the U.S. got into the space race. Okay? Russia jumped out ahead. They were the first to get a rocket into space. They were the first space. They were the first to send a cosmonaut into space, like our astronauts. I think they were the first to circle the globe. Okay? They were beating the pants off of us, you know. Not far ahead, but just beating us every time. Well, under John Kennedy, in the early 60s, we are going to get to the moon first. They beat us in everything else. We're going to get to the moon first. And they started the National Aeronautic and Space Administration. What was that named by? NASA. They started NASA. I don't know where the trash can is. I don't know what it is. Okay. But they started NASA. And so to begin with, because we had to beat the Russians to the moon, you know, because they beat us everywhere else, they basically were given almost blank checks. Okay? So they got to spend money. They were careful with it, but they planned everything. They controlled everything. They did the thinking. They hired the people, you know, did the stuff. And we had a pretty successful space program. We had some errors. We had some failures. We had some explosions. We lost a few lives. But by and large, in Russia, who knows how many they lost. There was just, people weren't as important to them. But anyway, sometime after that was over with, we beat them to the moon. Russia was, or Soviet Union was weakening now. They weren't as big a competition. So Congress said, wait a minute, we can't afford you to spend all this money on this. You're going to have to cut the budget. And you're going to have to farm out. We've got universities. We've got national laboratories. They can do some of this work for you. You farm it out to them. So for the first time, and it happened to be the project that was on deck, you know, ready to go, was a probe to Mars. I think we had sent some other things to Mars. They're going to send this Mariner probe to Mars. Yeah. So there was a lot of calculations to be made, a lot of steps in the process, but they weren't going to be given enough money to do it themselves, so they had to have bid it out to other people. So one group decided to do the launch. Okay, they won that bid. Another group got us out of getting into space, going into orbit of the Earth. Another group got us to go from the Earth to Mars. And then another group was going to get us in orbit around Mars. And then maybe another group was going to take all the pictures and make all the measurements and do that. So that was all done. So they farmed it out. And this was the cheapest mission NASA had ever done. They were trying to save money. $6 million. I'm going to make it up. I don't know. It had been $6 million. I don't know. Some number like that, much cheaper than anything else had ever been. Let's make it $6 billion. That's probably closer to true. Okay? We had a perfect launch. The first team did their job. Okay? The next team that took us out of launch and into orbit, perfect. Everything worked perfectly. The next team took us out of orbit and sent us to Mars. We made that transition beautifully. And then the next one was to take us to travel to Mars and go into orbit of Mars. As soon as it got into Mars' atmosphere, it turned and crashed into the planets. What went wrong? Everything had been perfect up to then. They investigated and found out that this team used one set of units. This team used another set. Someone forgot to label the units. And they assumed they were on the same page. And one of them was using metric and one was using U.S. customary. And they just assumed the numbers they were reading were whichever one wasn't. And there went $6 billion down the tube. Just because someone didn't put the units down. So that's sort of important. Units are important. So that's why I got into that story. I'm not sure it was $6 billion, and I hope that someday you're in a position you can make a $6 billion mistake. But I hope you don't make it just because you didn't put the units down. So, anyway, we're looking for force. There's the acceleration of 6.00, precision there, meters per second. And what's the other thing we know? The mass. And what symbol do we use for mass? M is equal to 5.00 kilograms. Okay. So here's what we're looking for. This is the unknown here. Here's what we know. Is there any relationship that ties what we're looking for to what we know? What is it?
The equation
Yes, and what was it? M times A. MA. Force equal mass times. Remember that. F equal MA. F equal MA. That's one of the fundamental formulas in physics. Okay? So, plug and chug now, folks. The force, net force, is mass 5.00 kilograms. Don't forget your units. Times acceleration. Oops, I don't need to write an A there. I write a 6. Oh, no. 6, yeah. My pen's not working. There we go. All right. 6.00 meters per second squared. And what does that come up being? I thought you can do that. I think you can do it in your head, can't you? 30, but we got to put 3 significant digits. So 30.0. What units? Kilogram meter per second squared. You multiply the units just like you multiply the numbers. But we know what a kilogram meter per second squared is. What's that? Named after Sir Isaac Newton. 30.0 newtons. I've got too many little dots in there. Let me see if I can erase some of those. Okay, there we go. All right. There's our first problem. Good job, folks. Okay. Next example. Y'all got it? The first one? Okay, I'll let you get it. All right, good deal. Example 2. Can I erase this? All right. Example 2. What force? That sounds a lot like the other one. So what we're looking for, net force. What force? That's the unknown. Is necessary to produce an acceleration, ACC. What symbol we use for that? A of 2.00 feet per second squared. Ooh, what units are we using now? These are U.S. customary, not metric. Feet is U.S. customary, or British or English, however you want to call it. On a mass of, and here they did it, and mass was what? M. And here I told you, maybe it'll show up sometime in the book, but it's really a mass of 3.00. Guess what? Oh, is it 2? Yeah, the other one's 2. The mass is 3.00. Anyone got your book? Slugs. I told you you wouldn't have many of them, but I said the book may throw some at you just to get you used to them. So guess what force that will be? What's the formula? MA. And the M is? Yeah, which is? 3.00, good old slugs, you don't even have an abbreviation for it, times acceleration of 2.00 feet per second squared, and those multiply to be 6.00, need 3 significant digits, and what's a slug foot per second squared? That is a, what do we measure force in U.S. customary? Pounds. Force, weight, pounds, okay? Your weight is your force due to gravity pulling you downward. That's what weight is, okay? So that's measured in pounds. I don't even like to write slug foot per second squared. That's so long to write, just put pound down. Okay, 6.00 pounds. Ah, that wasn't bad, was it? Okay. Okay. Second? Yes.
So, on the test you want, it wouldn't matter if we did the pounds, or it wouldn't matter if we did, if it's easier for us to remember to put slug foot.
Oh, if you put correct units, whether it's slug foot per second squared or pounds, I don't care, as long as they're correct. Okay. And, yeah. Okay. Yeah. you could write this as 6.00 slug foot per second squared. Yeah, just like kilogram meter per second squared, slug foot per second squared. See, second is the same in metric or U.S. customary. Later, when we do electricity, because electricity really came into being after the French came out with the SI units, so then everybody used the same thing. So ampere is used in both U.S. customary and thing. Seconds, that was so common, everybody continued. They couldn't cheat on seconds. You know, that was already determined. Okay, that was example 2. Let's move to example 3. You ready? Everybody got it? I'll leave it up there if you need it. Okay, got it. Got it? Okay. So let's erase this so we can go to the next one. And by the way, these will all be on YouTube videos once I get everything set up now. Again. Okay, this time it says find the accelerations. What are we looking for?
Acceleration.
A is the unknown here. Find the acceleration produced by a force. And what's the force? The symbol for it? F sub n, that means net force, of 500 newtons. Now here they put a little bar over that second zero. Here's what that means. Okay? As you saw before, anytime you have a decimal number with zeros after that, those are significant numbers, significant digits. When you have a big number like 500 with zeros after it, that could be one significant digit, because zeros, you can't tell if they're rounded or not, or 2 or 3. So how you determine if these are significant if you have a bar over. If you had a bar there, that would be just 2 significant digits with the last one not being. This says that this one and that one are significant, so the ones in between have to be. So that's 3 significant digits. The bar means that 0 is significant. Okay? So there's the force. Now, I also want you to remind me what a force is, what a Newton is. What's that unit equal to? A Newton is there's a method for my madness here. What is a Newton? A kilogram meter per second squared. Now that's not a minus sign, that's a dash, meaning you multiply those two. Okay? So that's what a Newton is. Okay? There's a reason for that. And it says applied to a mass of, so mass is symbol, it's M, is equal to 20 points. Okay. When I move this, it sometimes flashes out. It'll come back. Sorry. Because when I write on this, it collapses sometimes. Of mass of 20.0 kilograms. This is a lot more massive than the other ones we're talking about. Okay? So, we're looking for acceleration. We know the force. This is F sub n. And we know the mass. How do those relate? The mass is 20 kilograms. Is that what you're asking? Second? I think you may have said it right. I didn't hear. Yeah. Okay. You said A is equal to F sub n divided by M. Is that right? Yeah, you got it. Triangles and circles, yeah, that's what we got. Or you could go back F equal MA and divide both sides by M. And you got it. Okay? So that will be 500. And see, I could put Newton down there, but the reason I did this, so I could put down kilogram meter per second squared. You'll see why in just a second, I hope. And the mass is 20 .0, that third zero is significant because it's after the decimal point, kilograms. Now you see, I hope you see why I put this down. The kilograms cancel out. All right. That deals with the units. Let's do the division there. Okay. Now, I like to do my maths in sort of a short order, but if you want to do it more complicated, you got calculators, you can use them. What I like to do is move this decimal one place that way and that one place that way. 2 will go into 50, 25, but I need 3 significant digits, 0.0, and then the units are left, meter per second squared. And isn't that a great unit for acceleration? Yes, that's how we measure acceleration. Length per time, meters per second squared. Okay. What's that?
It's not that bad once you get an understanding.
Right.
Yeah.
All right. Any questions? You see how this works? And sure enough, they got it right in the book. Good for them. Okay. Now. Say that again. Yeah, this I'll put the first class and this one on YouTube video. The first one's already there. It's in the playlist, but you just can't access it because I forgot. Somehow it didn't get done, so I'll try to get it done. Say again. Okay, yeah, and I'll keep recording up until 6:30, so you'll be able to get it. Okay, but let me say this before you go, or you can go anyway. There, we finished 5.2, and 5.2 has problems. Number 5.1 didn't have any. 5.2 has it says find the total force necessary to give each mass a given acceleration. And because I'm going to give you odd problems. Why? Because the odd answers are in the back. So do any of the odds 1 through 7. Okay? And then number 9 through 15 says find the acceleration of each mass with the given total force. So do any of the odds 9 through 15. And then after that, do any of the odds 17 through 33. And basically what I tell you is do as many of them as it takes for you to feel confident. Yes, I've got this. Then go on to the next group. And then when you got those up, yeah, let's go on to some more. Okay. So I want you to say lots of, yeah. Okay. All right. All right. 5.3 now is talking about, I'll go on and erase this unless anyone needs it a little bit longer. Everybody got it? No, you got it. What's that? No, they are strictly for your benefit, so you can get the practice you need, because then when I give you the test, you already have all the skills you need. But you can also go back and look at the program.
I'm just trying to refresh, so I want to get caught up with my other teachers. Did you say the test is going to be take-home, right?
Yeah, y'all wanted that. I just didn't know why. Just kidding. Yes, they're all take-home tests.
Okay, thank you.
Okay. Number 1 is, guess what? Here's where I have reality. Or at least I try to make it sort of real. If you were working for me and I had a problem that I needed solved, I'm not going to say, here's the problem, close your books, and I want you to get it done in 3 minutes, or 15 minutes, or an hour, or something like that. No. I want you to have all the resources at your fingertips so you can look up what you need, make sure you've got the right conversions, the right formulas, you got everything right, because I want the right answer. Okay? I don't want based on memorization or anything else. That's what physics is solving problems. I'm confident the test bank is giving you problems that are going to be tough enough that you're going to need to look and study. And guess what? The test is going to be part of the learning process. You'll probably learn how to do this stuff. Unless you're really good about doing those exercises and get them all down, then the test is a piece of cake. But sometimes maybe you have to take the test and I have to go back and check this and stuff. You're learning stuff when you do that. Okay, so that's why I gave it. Take home. That's one reason. The other reason is we don't have time to have an hour test at the end of every chapter. That would take up so much class time we wouldn't get all the material covered. So those are the 2 reasons. If y'all don't mind. We'll be oh, you don't. I was afraid y'all were going to say, no, we demand in-class test. Okay. All right. Any questions? All right. All right. Say again. Okay. All right. To go to 5.3. Erase this? Everybody got it? Okay. All right. Okay, 5.3. We're going to talk about two concepts here. One, believe it or not, we've already talked about, okay? But the first of these is gravity. All right, take care. It'll be on YouTube. Okay. All right, gravity, and the other is weight. And these are closely related too, okay? Gravity and weight. We'll start with weight. The weight of the object, and you'll see what it is, the weight is the gravitational pull. That will be gravitational pull. What is a pull? A force. So that's the gravitational force, okay, on an object, okay? Now, we happen to live on the planet Earth. And I'd say most of the time that we ever spend, we're going to be on the planet Earth. We're not going to the moon anytime soon. I'm not. Okay, you may, but I'm not. I'm not going to Mars. I'm not going to Venus or Mercury or Jupiter or anywhere else. I'm going to be on the Earth almost my whole life. And even when I'm in a plane, I'm not very far from the Earth. That might seem like you're way up there, but you're really close to the surface of the Earth. And even if I was in a submarine in the Navy for a little time, even underneath the water, it's still right on the surface. I mean, you're awfully close to the surface of the Earth. So I'm going to spend my whole life right near the surface of the Earth. So the gravitational pull is going to be constant, okay? Going to be constant. Now, for those people who do go up into space, the further they get out, the less gravitational pull you have. That's why they have to fire those huge rockets. You have to force that spacecraft to get out of the gravitational pull of the Earth, and that takes a lot of energy to do so. But once they get up there, they just circle. You know, it's not much energy required after that. Everything's required to go up. Okay? Now, so that's what weight is. The amount of gravitational pull exerted on an object by the Earth. Okay? That's on an object by the Earth. Okay. Now, that's assuming you're on the Earth. For those people who went to the moon, it's a gravitational force exerted on them by the moon. Or, if we ever get someone to Mars, which I doubt, but if we do, it'll be the gravitational force by Mars, okay? Or wherever we happen to wind up, okay? Now, I wish they had a picture of this because I can't draw it, okay? But I want you to imagine this. I'll do something better. They show a brick. I don't have a brick handy, so this actually is shaped more like a brick, so I'll use this. A little brick, okay? Now, believe it or not, I'm exerting a force on this eraser. Do you believe that? Yeah, because if I release my fingers, it's going to fall. Gravity is pulling it down toward the center of the Earth at all times. I can hold it like this, and it still goes downhill. It doesn't go downhill. So gravity is always pulling toward the center of the Earth. Always. To keep anything from falling, you have to exert a force to keep it from falling. Now, if this were a brick, I know I was exerting a force. This is pretty light. It doesn't bother me at all. If this was a brick or a concrete block, you know, I would really be struggling to keep it up here like this for very long. I'd want to let go of that thing. Okay. So I'm exerting a force, but as soon as I release that force, there it goes. Now, so there is a pull. That's weight. It's a force. What were the units we used for the the U.S. customary system for force? Pounds. And what do we use for weight? Pounds, because we're measuring the force that the Earth is pulling us downward, right? That's what we are measuring when I step on the scale every Monday morning. I try to remember to, just to see how bad the news is. But, okay, it was, that's what The weight I register there is the force by which the Earth is pulling me down. Okay? Now, what can you tell me about those astronauts up there in the spacecraft? They look like they're weightless.
Yeah,
They're not quite, but they are almost. They float around. And if they had this, what did I do with it? There it is, okay? If they had this and dropped it, it would just keep going. It would fall because they're outside the gravitational pull of the Earth, or at least for very much of it. Okay? Now, one of the astronauts, when they went to the moon, took a golf club, a golf ball, and he swung that thing. That ball just took off and went. I don't think they ever were going to find it. They weren't going to need to try. Because two reasons. Gravitational pull of the moon is much less than the Earth. Number two, very little, no air resistance on the moon. So it just took off and went. So, longest tee shot ever. Okay, never mind. Okay. So, and he wasn't that good of a golfer. Okay. So that's what you have. Now, what would you say? I know it was really hard to follow. But right when I did release this, at the instant I let go, what is the velocity of that? What's the velocity of it right now? 0. It's not moving, right? As soon as I release it, it's going to increase its velocity, starting from 0, and then believe it or not, it's going to speed up all the way down. Now, I don't have a tall enough ladder so you can do that. I have done it a time or two over on the Bassman campus, get up on the 3rd floor, drop something out of the window, and it's going pretty fast by the time, that it got to the ground. Okay. I didn't mean to drop you. Okay. Now, the velocity of the falling brick increases because gravity is pulling it down. Whenever you have a net force, what do you have? Acceleration, absolutely. Anytime you have a net force, you're going to have an acceleration, meaning the velocity is going to increase. So it went from 0 to whatever speed it was right before it hit. Okay? And if I took it higher up, it would get at a faster speed before it hit, up to a limit. Okay? So here is the formula we use for weight. Okay? Now this book uses F sub W. Other books will use different things. It's a force. Weight is a force. The little w means the weight force. N was the net force. This is the weight force. The weight, the force of gravity pulling you downward, pulling whatever it is downward. So this is the weight is equal to the mass times, guess what? An acceleration, but this is a very special acceleration. This is the acceleration due to gravity, so we give it the symbol G. Okay? And because it's the same Earth under us everywhere, and we never get very far from the surface of that Earth, okay, this is a constant, considered to be a constant throughout anywhere on the surface of the Earth. So G for the Earth, I'm going to give it to you first in SI units. It's 9.80 meters per second squared. Remember, it has to be an acceleration. That's the acceleration due to gravity. Now, people get lazy. I get lazy sometimes, call it gravity. It's not gravity. It's the acceleration due to gravity. It looks like it would be 9.80 meters per second squared. In the U.S. customary units, G is 32.2 feet per second squared. That's the acceleration due to gravity on Earth in the U.S. customary system. Now, just looking at that, you see it's about a little more than 3 times as far, right? Fast, right? Well, that makes sense, doesn't it? Because remember, A yard is 3 feet, and a meter is just a little bit longer than 3 feet. So therefore, the acceleration would be a little bit more than 3 times this, and 3 times 10, this is awfully close to 10, would be 30. A little bit more would be 32.2. Now, a lot of times in common literature and stuff, you'll see it rounded off to 32. They'll say 32 feet per second squared. A lot of books use that. This book uses 32.2 feet per second squared because they like to have 3 significant digits. Okay. That being said, let's go to example 1 in this section.
So you're not going to give us the definition for gravity?
Say again? Oh, gravity, okay. Gravity is the force that the Earth pulls down, pulling down. So gravitational pull, basically, that is the pull that the Earth is doing. Weight is the measure of the gravitational pull, okay, or the force on an object. Okay. Everybody got this? Can I go to erase the slide? Okay.
And this is 5.3, right?
This is 5.3. You're right. Okay. Find the weight. So we're looking for weight. What symbol do we use for weight? I'd like to use W. They use F sub W. Frankly, you'll find me putting W because I'm used to using W. This book uses F sub W, which means the force, the weight force, okay? Of, so this is what we're looking for, of 5.00 kilograms. They didn't tell us what that was. What is 5.00 kilograms? What it's got to be? What is measured in kilograms? Second? Mass. That's what we measure in kilograms, mass. So there's your mass. They won't always say of a mass of 5.00 kilograms. They said of 5.00 kilograms. You have to recognize that's a mass. Okay? Have they given us enough? Second? Okay. Yeah, and what is the acceleration? What acceleration are we talking about? Due to gravity. And we know that one. Did y'all ever see Wicked? Oh, okay. You've heard the song, though. Oh, you haven't? I can't sing it, but it's something, I believe in gravity, or something. No, I can't. My wife likes the song. I don't know it. Okay, never mind. So G, what is G? And what units are we in? The giveaway is that kilogram. What system are we in then? Okay, what system are we in? Okay, we're going to wind up with force in newtons. You're absolutely right. What system does that mean we're in? SI. That's the SI unit. So we need to get gravity in the SI unit. And what's gravity in the SI unit? 9.80. You're absolutely right. 9.80. What units? Okay. I'm glad you said that in a sense. Meters per second squared. Notice here how we use letters for different things. The parameter, M, stands for mass. The unit M is meters. Okay? And the symbol that precedes a unit, little m, means milli. So it could be millimeters, milligrams, yeah. So you use all sorts of things here. Okay. So there we have our acceleration due to gravity. So can you give me the weight? What's the formula? Okay. Mass times acceleration due to gravity. F equal ma. Here it's F equal mg because you're talking about weight. Okay. The other was net force. This is the weight force. And what's your mass? 5.00 kilograms. And what's your acceleration due to gravity? 9.80. What units? meters per second squared. Okay, you multiply that out and you get yeah, you waiting for me to do all the work, huh?
Oh, 49.
Second.
0.
49.0. You got to have that third significant digit in there. And what units will that be?
No, it'll be second with the kg.
Yeah, kilogram, meter per second squared. But you know what that is. What is that? Newton. Exactly. 49.0 newtons. Huh?
I'm learning.
Excellent. Way to go.
Why you say it has to have the extra significant number?
Because all your inputs were to 3 significant digits, so give the output to 3 significant digits. Okay. Now, you haven't gotten one yet that you have to do a division on your calculator. The calculator will show you 17 digits. No, it'll be 9 digits or 12 digits, however big your calculator is. You always round that to the appropriate number of significant digits. All these, we've actually had to put in things, but later we'll have some you have to round. Okay, that's what they got. Good for them. Now, oh boy, here's another one. You said, am I going to do it? Well, I don't do it. The book does, but here we go. Do I need to leave that up a little longer? Okay. Everybody got it? You still got it? Still writing?
Oh, no, I was just
Oh,
trying to
okay,
find
good.
the last one to
Okay.
Newton.
This is very similar. Find the weight. What symbol for weight? F sub W. Very good. That's what we're looking for. That's what it said to find, so that's what's missing. The weight of, and this one says 12.0 dumb book slugs. Okay. So, what unit must, what is slugs measuring? That is a mass measurement, too, that no one ever uses, but the book's throwing them at us here. So, what are we going to need to answer that question? Ah, excellent. That's the acceleration due to gravity in the U.S. customary system, and that's 32.2 what units? Feet per second squared. Perfect. Okay? So your weight, which is F sub W, is equal to what? 12.0 slugs. I have to write it out because there's no abbreviation for it. Times 32.2 feet per second squared. By the way, this is mass. This is acceleration due to gravity. Special acceleration due to gravity is always out on the surface of the Earth. This one, you will need your calculator, and you're going to need to round, I think. Yeah, you will. What do you get? 300, huh? 3 what? 86? 380, what?
386.4.
Okay, you said 386.4. What's wrong with that picture?
It's
More than 3 units. So what you do, you count your units from the left. 1, 2, 3, look to the right. That's less than 5, so throw it away. So this will be 386, what unit?
slug or pound?
Pounds, thank you very much. You could write slug feet per second squared, or it's so much easier to write pounds. Okay? Yeah.
Yeah, it's so simple. It's the easiest thing I could have learned all day. But It's just remembering the formulas and what goes with
Right.
Yeah.
Because I can see myself now simply get it wrong because I used the wrong gravity from,
Right. Yeah.
Yeah, that's why I'm glad he let us do take-home test.
Yeah.
I be in class like, oh snap, which is the formula? Which one is it?
So the 9.80 is the SI unit.
SI unit, that's the U.S. customary. And frankly, folks, that's why I asked those questions, because that's what I want you to think. Where am I? What units are we in? You know, what is this asking for? You know, what are the clues here? You know, All right. And the book got it right, which is so good for them. Okay.
We need to make a group chat now.
A group chat.
We need to pull up a group chat. Yeah.
And by the way, I should have said this before other people left. If y'all want to come take pictures of the problems that are in my book, so you can be working on, you sure can. Okay, if you want to do that before you leave tonight. I should have offered that to everybody else. If they'd have stayed here, they could have gotten the offer too, you know. Okay. You get rewards. Okay. No. All right. All right. Now, what I'm going to do here is move to my other slide set, because I finally got to this one in the book. Now, I'm now regretting something that I used net force F sub n, because this book uses F sub n for something else. So they called F just either F or F sub T for total force. Well, I was calling net force. Sorry about that. I forgot they use F sub n for normal force. Okay. Now I did this when I was holding the eraser. I told you I'm having to exert a force on it, because when I release it, it's going to fall. I'm not exerting any force on the eraser there, but guess what? The table is. Okay, because if it wasn't, it would be falling. Okay? Now, how much force is that table having to push up on the eraser? Not that much, because the eraser is very light. It's the weight of the eraser. The force due to the weight. It's not pushing up any more, or else it'd be flying off that. Okay? It's not doing any less, because it would be sinking. It'd be sinking into the table. It has to be exerting a force exactly equal to the weight. If that brick is sitting on the table and the table's not bending or breaking, then the table has to exert the same normal force upward as the brick is being pulled down. Because what's the net force on that thing? Yeah, because it's not moving. It's not accelerating, so the net force is 0. So here, net and normal, don't get these confused. This is a normal force up by the tabletop. Because it's not moving, the net force is 0, so therefore that must equal exactly the force due to gravity. Down. Exactly equal. Okay? And the normal force. Why it's called normal? Normal is another word for perpendicular. It's the perpendicular force exerted by that tabletop. And that's exactly opposite the weight force being pulled by gravity. Okay. Now, that's what they're saying. Weight force versus normal force. The normal force, F sub n, is perpendicular to the contact surface. So that's where the normal comes from. Oh, let me go back and get my... Okay. And that is force perpendicular to or normal to the surface. Y'all understand perpendicular, that symbol? Okay. This, of course, remember, was weight force. Yeah, this is 5-3. Still, we're almost through with 5-3. That's your weight force. Okay? And we know what that is, or the formula for it, right? The normal force will be equal and opposite to that. Same quantity, just different direction. Remember, force is a vector quantity. It has direction associated with it. Because it's not moving, the net force is 0, so therefore the normal force has to be exactly the same as the weight, only in the opposite direction. All right. Now, when you go to the grocery store, the scales that you have there for the produce, they usually have 2 scales on them, an upper one and a lower one. Have you ever noticed? The upper one is usually pounds, and the lower one is kilograms. Okay? But that's not really very fair. It's not right. Kilogram measures mass, pound measures force or weight. You shouldn't be using those as their equivalent. But guess what? We're all on the surface of the earth. So are those scales. They only differ by a constant, the acceleration due to gravity. That's constant throughout. Okay? So therefore, you can do that. It's not really very fair. Weight, mass and weight are different quantities. Okay? And here's an example of that. What did I say? I didn't tell you that. Okay. Unfortunately, my weight is about between 215 and 220 pounds when I'm on the surface of the earth. Okay. If I were to become an astronaut, which I'm not, and were to go up into outer space, what would move my weight up there? Very little. Basically zero. You become almost weightless. There's a great weight loss program, isn't it? Go into outer space, okay? And now you weigh a lot less. But when you come back, you still, okay. And you just hit on it.
They don't got no real food up there. They be eating air food.
Okay. But your mass doesn't change. Mass is an invariant. I'm the same mass here as I would be in outer space. It's just that the force due to gravity, the acceleration due to gravity, is less up there than it is down here. Now, if I was on, couldn't be on Jupiter because it's gaseous on the surface, but if I were, my weight would be even heavier because Jupiter is one huge, massive planet. Yes?
What planet is almost the same equal amount, like, as gravity is?
As we have?
Yeah.
Venus gravity would be very close to us because they're about the same size. We're actually a little bit denser and we're a little bit bigger, so acceleration due to gravity on Earth would be a little bit greater than
So
that.
Earth died, we're going to Venus.
Okay. You don't want to go there. Okay. She thinks men are from Mars and women are from Venus. The trouble is Venus, it's incredibly hot.
Yeah, I knew it was one of those hottest on the way.
Yeah. And they have a very dense atmosphere. It traps all the heat from the sun.
We'll dig underground or something.
It's probably getting even hotter there. Okay. Yeah, Venus is incredibly hot and it's incredibly hostile too. The atmosphere has almost no oxygen in it. It's sulfuric acid and things you couldn't
Yeah,
breathe.
they'll be categorized Pluto as a planet no more. We'll
No.
freeze out there.
It's called a dwarf planet now.
Yeah, we'll freeze there. So
Oh goodness, yeah, that's so far out there. This is just incredible. We are just in the perfect place with the perfect atmosphere, perfect everything for life.
Messing it up.
If you mess it a little bit, you're gonna mess it up. And this global warming thing, people act like it's not a big deal.
It is.
Goodness, we could be getting near a brink of something we just don't know what. Yeah.
Somebody asked me what I could change in the world, and I said, why don't we make the United States recycle? You know how in Asia they make people recycle, like it's mandatory that they recycle.
Oh
Like
yeah.
every last little thing that they have, they gotta recycle. Why don't we recycle as the U.S.?
Well, I do. I mean, I drive my wife crazy
It's not
sometimes.
mandatory like it is in
Yeah.
Asia.
Yeah, because we're used to in the U.S. of freedom.
Right, and then down south, like, it's so much different. Like, if you go up north, like Detroit, New York, like, they will literally try to beat you up throwing away a bottle because they get money back in New York. Like, they can drink a 2 liter and go back to the store and get, like, 20% off their next 2 liter with the old one. It's just down here they don't recycle.
And if you made it cost, that's the only thing that makes Americans respond is moolah. You know.
I don't see why we ain't just go.
I threw away one drink can in Detroit and they was like, they went so crazy I knew not to throw anything else.
I recycle everything. In fact, if I drink a drink here on campus and there's no recycling here, I take it home. In fact, boxes, when I get books, I take it home. My wife says, quit bringing that stuff here. You know, we have to. But I just can't stand not recycling when something I can. And it really irked me when they took the. Right now, they only recycle number 1s and number 2 plastic. So 3, 5, 6, none of those they'll take anymore. But in fact, they're not taking glass much anymore either, which sort of irritates me. But
That's crazy. Yeah. I'm really big to Korean culture and all that, and I watch them, they'll go through their trash.
Right.
How we'll go through, how people I'm not going back through our trash.
Yeah.
No, they literally go back through their trash and put the stuff where they supposed to put it,
right,
and take it to the place where they gotta recycle.
I mean, I'm all for recycling, but I don't like bugs and stuff. So
you like what?
cans and stuff like that. It really be a waste of time. Really trying to recycle.
We have a. Yeah, we have a recycling bin we set on our porch, and everything goes in there. And when my wife doesn't want to do that, she puts a bag right next to the trash can, and the trash goes in the trash, and the recycling goes into the bag. That way, she doesn't have to. She just does it when it does, and doesn't have to walk out to the porch and put it there. I'll walk out to the porch. I need to walk. Yeah. But anyway, yeah. And my sister-in-law and her husband, he was a dentist in the Army, and they were in Germany for a few years. Boy, they were really strict on recycling there too. Yeah, you got it right. Oh boy. Okay. So let's move on. Mass versus weight. We talk about them as if they're the same, but they're not. Okay. There's sort of a little problem here. For example, an astronaut who has a mass of 75 kilograms. Let's move to another page. Okay, whoops. Didn't mean to do that. Discard. Okay, and go back to this one. Okay. All right. So the astronaut has a mass of 75 kilograms. Let me get my pen back. I hate it that they do this. M is equal to 75.0 kilograms. Okay? What would be the weight of the astronaut? What question do you ask yourself? What units are we dealing with? What system? No. Kilogram is SI. This is SI. So in the SI system, what else do you need to know? Yes, the acceleration due to gravity is 9.80 meters per second squared. Okay, so the weight would be 75.0 kilograms times 9.80 meters per second squared. And this one, I think we're probably going to have another round off here, so let's do it. I don't have a calculator. I'll let y'all do that for me. It's going to be something 735. You've already rounded, huh? Oh, it didn't have a round because 8 times 5 is 0. Okay, 735 what? Second? We need units. Don't have just numbers hanging there. You might make $6 billion mistake. What unit? You could do, if you didn't remember the unit, you could write out kilogram, meter per second squared. Or if you remember that, that was a Sir Isaac? Newton. Okay. Or Newton, either one. Okay. All right. Now, that's what her weight is on Earth. This is a female astronaut, I think. Say again?
Did I add that up wrong?
I don't know. I was taking your word for it.
75.0 times 9.
Yes. Oh, yeah. She's making fun of my writing. I'll remember that. No, I'm just kidding. Okay. All right. Okay. Now, if that astronaut lands on the moon, where the acceleration due to gravity is less than that on the Earth, the astronaut will have the same mass, if she hasn't, lost any on the way, and usually they don't, but will weigh significantly less than 735 newtons. It has an acceleration due to gravity of about 1/6 of that of the Earth. The full explanation, blah, blah, blah. Okay. So, example 3, do we have time to do it? I hope we do. Ooh, can we do it in a minute? Maybe not. Let's try it. Okay, example 3. Find the 75.0. That's still the same, so I don't have to write that down. Astronauts' weight on the moon, where G, now G on the moon, this is G on the Earth, G on the moon is, in SI units, 1.63 meters per second squared. So what would her weight be on the moon? That's weight on the moon. Same mass, 75.0 kilograms times 1.63 meters per second squared. Okay, it's 1.63. Is that what you're asking? I can't hear. Oh, okay. What's the answer? Okay. Too many digits there. That's it, because that's the 2 is less than 5. Okay. 122. What unit? No! Kilogram meters per second squared, or newtons. Okay.
Yeah, I got it. I just got to get that down. So.
Okay. 122 newtons. Okay, slugs, you get pounds, right? Is newton. Yeah, exactly. Because the seconds are still seconds. All right, and you're right. The mass remains the same, but her weight, whoa, boy, did she ever lose some weight. She went from 735 newtons down to 122 newtons. Whew. Okay, yes. At the end of the chapter. And this chapter we're almost through with 5.3, and we got 5.4, 5.5, and 5.6 really doesn't have any problems. So I should have it ready for you next time. Yeah. Is that all right? Okay. All right. Good deal.
Don't forget the syllabus.
Yeah. Here's the and the link to YouTube. We still got example 3 to go, so let me mark that before I forget it. No, we just did example 3. We're going to start next time at mass versus volume. And now, we've finished all the problems in 5.3, so you can do either 1 or 3, or both if you want to. Any of the odds 5 through 9, and then any of the rest of them 11 through 29. Okay? Plenty to work with there. Okay? All right, good deal. Any questions? Good class. Y'all are a good group. I'm looking forward to this term. And it doesn't look like we've lost too many people, maybe, so we'll see.